So section P5 says we are going to solve equations graphically. That's why you need a graphing calculator today. And numerically, which is, well, sometimes we will use the calculator to do that. Other times we're going to go ahead and do the algebra. And that's the key anyway. You know, in here, if you don't show the algebraic thinking through a problem, you're not getting the points. That's just how it is. Pardon me. So we will be able to solve equations graphically, just reminding you of all the stuff that the graphing calculator can do. We've got the trace button that has the intercepts and the zeros and the intersections and messing with the windows and all that kind of stuff. We're going to do that today. And then solve equations algebraically, linear, using properties of algebra. We've really already used that. You know, that was in some of the other prerequisites. Then, if we want to solve quadratics, remember quadratics have a power of 2 as the highest power. That's called this degree, and those are parabolas. We're going to try to solve them by factoring. If all possible, we want to factor, because that's the easiest way to do it. But we may end up having to extract roots, which means taking a square root, but this book uses the fancy word extracting. And that brings us to completing the square and the quadratic formula. And we will not get to solving equations numerically using tables. We'll probably get through maybe one example of completing the square and have to call it a day. Now, note below here. Oh, smart board. Be a nice smart board. There we go. While graphing calculators will be used quite a bit this year, what we're using those for is to double check that we're doing things right and to get a visual of what we're doing. So our emphasis is on the algebra behind every problem. Feel free to verify your solutions with the calculator, but don't rely on it. In fact, there are 3 or 4 tests where we actually take your calculators from you, and we have to do a non-calculator portion of the test first, and then we give them back to you for a second portion of the test. Like it says, use very little in calculus. It's all about, can you show the work, can you show that algebra behind it. And always try to picture what the graph should look like before you grab your calculator. Because I make mistakes when I put stuff in all the time. So if you accidentally hit the wrong button, then away it goes. And if we don't think about what it was that was supposed to show up, and that thinking goes back to if we have an even degree, and that's our polynomial, we want to look at that and the leading coefficient to figure out, okay, this is parabolic, but is it going to open up or is it going to open down? And then we want to look at the odds and say, all right, well, this is an S curve, but which way does it go? Because does it have a positive leading coefficient or a negative leading coefficient? And we want to use that to develop that mathematical common sense. Did I punch something in wrong? You know, you could verify visually. Oh, well, that's what I think it's supposed to look like. Otherwise, wait a minute, I better go back and punch that back in because I think I messed up. So, solving equations graphically, this first example is really silly. To solve an equation such as 2x minus 5 equals 0, yes, that's one we definitely need a calculator for there. You can graph y equals 2x minus 5 and find where y equals 0. That is called the x-intercept. And yeah, we're going to do that just because, you know, we're trying to remember all the buttons and everything on the calculator. So it says use the 0 or intercept option on the calculator because what we want to find is this right here, the x-intercept, that little blue star looking. That's what we want to find. And like it says, verify the solution algebraically. Well, take a look at it. It's 5 halves. I mean, we know that. But let's get that in our graphing calculators. So that one was y equals 2x minus 5. Yeah. I better put it out of here and start over like you guys will be. First off, we did use stat plots yesterday, and stat plots don't necessarily allow you to do all this graphing, so you need to turn those off if you haven't already. Second, stat plots, number 4. 4 will turn them all off. And granted, we only use 1, but this way we're sure everything is off. And then y equals, and then this little bugger was 2x minus 5. 2x is right next to the green alpha key, minus 5, enter. Now, it's a line. We know it's linear. Probably a pretty good shot here that we'll see under zoom 6, which is that negative 10 to 10 window. We'll see exactly what we want because we know the y-intercept would be a negative 5 there. So that's what we see. And what we want to find is this little spot right there. Now, window is fine for this. But we might want to say, hey, let's take a little closer look at just that spot. I don't think I need to go from negative 10 to 10. Maybe I'll go from negative 5 to 5. So I go into my window, and I just change my x's and my y's so that I'm seeing a closer up view, a zoom view, and hit graph. Looks like 2.5, but looks is not what we're going for. We're looking for is it. So whenever we need the calculator to calculate anything that's up here on the screen, we're going to hit second trace, and that's because in the little blue letters up there it says calc. And now what we're looking for is the 0, which is number 2. And it starts prompting us. And here's Blinky. He's our little pet cursor. And Blinky says, is this the left bound? So what Blinky's trying to get us to understand is, this is the intersection, this is to the left of that intersection, and this is to the right. The calculator doesn't understand above and below, it only knows right and left. So I'm going to try and get a little closer to that intersection, because the closer you are, the less math the calculator has to do, so it shouldn't take it so long. That looks like it's just to the left, and I hit enter, and then I use my right arrow to go just to the right and hit enter. And it says, do you want to take a guess? You know, it's giving us a question mark. I wouldn't be using a calculator if I wanted to guess, so I'm just going to hit enter through that. There it is, 2.5. 5 halves, exactly what we expect. If you have your table going by 5s, yes. But for most people, it won't. We'll go through all of that stuff, to be honest. Hang in there. Yep, the table features. Yep, you can do that too. We're going to go through all of that today. So, lots to refresh memories on here. Alrighty, we had x equals 5 halves, 5 halves 0. But really, 5 halves is the answer. We were just trying to find out, you know, where is it 0, and we go through there. Now, this says, how about solving by finding the x-intercepts? And this one is not linear. So this one is something that if we couldn't factor it, we would want to figure out where those zeros are. And it says anyway, go ahead and use the graphing calculator. So solve the equation 2x squared minus 3x minus 2 equals 0. First thing I'm thinking of is, this is a parabola because it's a degree 2 polynomial. And parabolas have either no solutions, one solution, or two solutions. So I should be able to see that. We got to plug it in. They want us to plug it in. Don't worry about the algebra just yet. Plug it all in. And that was 2x squared minus 3x minus 2. 2x squared minus 3x minus 2. One thing to be careful of is not to accidentally use the negative button instead of subtraction. Calculator yells at you. Don't do that. Should be a pretty standard parabola. We ought to be able to get away with negative 10 to 10. So zoom 6. There it is. And what we want are the zeros right here, those x-intercepts. So now we'll go back into second, calculate. And there's actually a couple of different things we can do here, but we want the zeros right now. So we'll hit 2. And this is where things get a little sticky. People are like, well, now where's left and where's right? It's the same thing, but notice if I hit the left arrow here, now I'm to the left of that intersection with the x-axis. So that's what it means by left. I hit enter, and then I right arrow for a little while until I'm sure I'm below, and that's actually the right side of that intersection, and hit enter to guess. And that one says we are at negative 1/2 0. Cool. But we still need the other one. So second trace, number 2. And now we got to get Blinky over here. The difference is, now when we're below it, we're to the left. And that's because this is the intersection and this is to the left of that. So we hit enter. give it a couple of right arrows, enter, and enter to guess. And that one's 2, 0. So those were pretty basic, which tells me this was factorable. And we didn't necessarily have to use the graphic calculator for this. Don't clear it out. They have some other things they want us to do. But so far we have, bless you, negative 1/2 0 and 2, 0. But if we're going to solve it graphically, we need evidence of what we saw. You know, we can't just say, oh, teacher, test question number 2, come on over here, take a look. You got a graphic for me. So we need to make a table to verify what we know about this parabola. We already have our negative 1/2 0. This graph is a little high and weird today. We need some more. How do we get it to show us the table? Second what? Second graph. Now we're not going to graph 25, so that y sub 1 of 25 we probably don't need to write down. Negative 212 might be helpful because it tells us, you know, something to aim for to show the steepness of our graph. Negative 1, 3 would be good. 0, negative 2, 1, negative 3, 2, 0, 3, 7. Those are all good numbers. So I go back here and write them down. And then graph those points. You know, negative 212, like I said, it's just going to give us something to aim at. There's somewhere. Negative 1, 3. 0, negative 2. 1, negative 3. Boy, this is graphing high now. 2, 0, which we already had, and 3, 7. I am not sure that 1, negative 3 is the lowest point on that graph. I mean, on the table, it looked that way, but I am not absolutely positive that that's the lowest point that this graph goes. So I would go back to my graphic calculator, and I would try to remember, what do we do when we want to find that little spot right there, just so we can be absolutely sure. Do you remember? What do you do? Sure, you can't talk to me. You're already doing it. What are you doing? Nick? Second trace, minimum. Yeah, if we're looking at an up-opening parabola, number 3 is going to give us that vertex down at the bottom. So again, we're going to go ahead and go to the left of the valley. Press enter. Right of the valley, and press enter. And you may have noticed you're not pressing in exactly the same spot I am, but you're getting the same answer. What you want to do is stay as close to that intersection as possible, or as close to that minimum as possible, because the graphing calculator is actually doing math. And if you are messing around and giving it too large of a window to look at, that takes it longer to do math. So looks like just about 3/4, 3.125. So we didn't have the lowest point on the graph before. So 0.750 and negative 3.125. And let's see. Be about, there's that. Because pre-calculus is about precision. You lose points even if you don't put the arrows on there, which, by the way, is a huge deal, because that's saying that you think that a parabola stops, but it's not going on forever. But it doesn't. Those arrows indicate, okay, this is going on forever. So every little piece of that is important when we're solving things graphically. So now, we've discussed a nice little parabola here. What about some others? Well, when solving graphically, if your equation is not set equal to 0, we can still solve it. you could set both sides of the equation as separate y equals equations, and you can look for where they intersect. The one problem with this is interpreting the answer, because what we're really trying to find is the intersection of these 2 points. So we're going to graph y sub 1 and y sub 2, and we're going to see where they hit each other. Now, we only care about the x answer, and I'll show you why once we have this up here. But that means we have to remember how to graph absolute value. Does anybody remember where we go for absolute value? I don't know. So we got it? Math, arrow to the right once for numbers, number 1. Good. Many people remember where that was. What is. So what we're going to do is we're going to put the absolute value of 2x minus 1 in y sub 1. X minus 1. Out there. And go down to y sub 2. And then 6. And I'm going to stick to the old Zoom standard, Zoom 6. Now what we're looking for are the x values here. Here's why. Notice, they are going to intersect at 6. That's because we just told the calculator to do that. We said, when is this going to be 6? So the answers that we get, we really only care about the x coordinate for these. But again, it's going to be second trace. This time it's intersection. And let's get our pet Blinky over to the left so Blinky knows that's where he needs to go. Come on, Blinkster, behave yourself. Alright, enter. And then we see Blinky jump, and we know, yep, now it's on the green one, that's what I want. And hit enter to guess. Negative 5 halves, 6. So our answer is negative 5 halves. X equals negative 5 halves. And then we need the other one, so second trace. Number 5. But now, this is always the time I wish that calculators had some kind of elevator music or something. Maybe the Jeopardy tune. Come on, Blakey, go. This is what I wish I had my TV calculator back. It took all the TVs and they didn't tell us they were taking the TVs. I liked my TV calculator. 3.5, 7 halves. Again, they both had a 6 for y because we told the calculator to do that. We said we want to see when is the 6. So it's really just the x coordinates that we were looking at. So if that bothers you, remember you could always move it over and then find the zeros and do it that way. But what we wanted to do was find those solutions. And that was at negative 5 halves 0. Oops. And at 7 halves 0. So that's using the graphing calculator. And that is just silly because we know how to do this. We did this in Algebra 2. We know how to solve absolute value. Absolute value of 2x minus 1 equals 6. I want you to think that way. Here's what I want you to think. The absolute value of something is 6. And that could be 6 that way. But that could also be 6 that way from 0. So we could have 2x minus 1 equals negative 6. Or 2x minus 1 equals positive 6. Those things can happen. Now, years ago, when we asked our Algebra 2 students to come up with a story or something, because everybody always forgets this and they just give one solution. One of the students came up with a really good one. He said, think of those absolute value bars as jail bars. If you're a criminal and you're trying to break out of prison, you don't just plan one escape route. You always have a backup. So you got one going this way and one going that way. Notice, by the way, we do this according to the number line. So the -6 is over here, and the +6 is over here. It's a good way to remember, hey, if I'm going to take those absolute value bars off of there, I need both of them. And then, of course, we add the 1, and we divide by 2. Add the 1, divide by 2. There they are. Exact same answers that we had with the graphing calculator, which, again, is showing us, if you have time, verify your answers on the graphing calculator. But most of the time, our tests are scrunched into the time slot we have as it is. But if you're ever thinking, gosh, I'm not sure about this one, just take a second, look at your calculator, and make sure you're doing things right. When solving equations by finding intersections, the value of the intersection point at the y is irrelevant. It doesn't matter. I mean, we're putting that number in. We're trying to make the calculator do the math for us. The solution is the x value. It's something more complicated like this, where what we're doing is we're taking an absolute value b, and we're trying to see where that is going to hit a parabola, x squared minus 4. They're unique. When we were doing the absolute value problem before, both of the y's were 6. We made that happen. For this problem, that's not going to be the case. This b is not going to hit x squared minus 4 in 2 spots that have the exact same y value. It's not going to happen. So with these, we'll actually write them down as an open pair. So we're going to do y sub 1 and y sub 2, and we're going to find where that absolute value b smacks into that parabola. Well, I've already got absolute value bars, so maybe I'll use that to my advantage there. 0.5x plus 3. And then x squared minus 4. Now, absolute value, we've probably forgotten something about since last year, but with x squared minus 4, we should all be thinking, well, that's your standard parabola, just move down 4 units. That'll fit on a -10 to 10 window. So, zoom 6 or graph, we should be able to see what we need. There's our absolute value v shape. And there comes our parabola. Yeah, 2 distinct intersections there. So, second trace. Number 5. And I'm going to get Blinky over here in the vicinity of the first intersection. Come on, Dexter. There we go. And then notice that he does jump to the other curve. It doesn't kind of look like it here, but second curve. Come on, Blinky. And you're on the green. No, you're not. Not even. There we go. So that one we would write down to 3 decimal places with rounding. So the ordered pair, -2.408, comma, 1.796. That would be that first intersection. Now I'll get rocking on the second one. Trace, number 5. All right. Blinky works much better with the mouse. I don't know why. I think the smartboard is a little bit slow, so it doesn't grab everything that I click. Come on, Blink. Now we're in the vicinity of the other intersection, so enter. Definitely see Blinky jumping down to the green here. Enter. Enter to guess. Ordered pair 2.908. Comma 4.454 with rounding to 3 decimal places. And I'll take that back to the other screen and write that down. I have my glasses on. Hoping this is really just on the screen. are the intersections of a V shape and parabola, an absolute value of a parabola. What are we finding here? Well, we're finding solutions, but there's more than one name for that. That's why this says, hey, these are all synonyms. They all mean the same thing. A solution is a root, is a zero, is an x-intercept. Why so many names? Because we have a name for each thing that we would want to use it for. If the problem says solve, then yeah, we're going to call it a solution. But every once in a while, as part of solving, you have to take square roots, and that makes it a root of the function. And then a zero, well, that's what they are. They're the x-intercepts. X-intercepts for graphic. You want to know, where is this going to land? So it says if you've got some real number, x equals a, and a function f of x, and you put a into that function and you get 0, not only is it a 0, it's all the other things you see on this list too. And then down here at the bottom, as it points out, that means a0 would actually be a point on that graph. It will be on there. So don't let the fact that they say solve versus taking roots mess you up. We're looking for the same stuff. And yippee, we're to the algebra now. Like I said, I really miss my TV calculator up there. So solving equations algebraically. We will focus on solving quadratic equations, which are parabolas in this section, since you've already reviewed solving linear equations. Oh yeah, we did that in one of the other prereqs. Quadratic equation in x is standard form ax squared plus bx plus c equals 0. Notice that it's equal to 0. That's our standard form. Where a, b, and c are real numbers and a is at 0. Because if a were 0, this would be a line. We want to study lines, we already did that. We want to study quadratics. If this is 0, this is gone, and we just got a line. So there are 4 methods for solving quadratic equations. You would love it if every single quadratic we saw this year were factorable. Not going to happen. It just isn't. But factoring is the easiest, nicest way to get those exact fractions that we want. We can also extract square roots. So extracting square roots. Your Algebra 2 book did not call it that. Your Algebra 2 book just said taking square roots. So we were taking square roots to find an answer. And that means we're going to have something squared, and we'll take the square roots. Then, completing the square. Absolutely. We can solve any quadratic by completing the square if we know what we're doing. In fact, that's going to be one that we're going to use pretty much the rest of the year whenever we want to solve quadratics, because you won't be completing the square in calculus, but the steps that it takes to complete the square are in the same wavelength and brain length as the things that you need to do in calculus. So we're going to spend a lot of time completing the square in homework assignments and in other assignments that we do. So, quadratic formula. I almost apologize for teaching you that. And that's because if you know how to complete the square, you really shouldn't need quadratic formula. So why do we still teach it? Because if you take an MCA or an ACT and you've forgotten how to complete the square, because it's a process, you've forgotten how to do it, well then the quadratic formula is your fallback. Everybody remembers the little song, and then they can get the answer right. Because it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And you get the answer right. You know, completing the square, people forget it. They do. We won't. None of us. Always remember completing the square. To solve by factoring, we need to use the zero factor property. This is also called the zero product property in a lot of books. What it says is this. If you are going to multiply two things together and your answer has to be 0, well then either this was 0 or this was 0. Because that's the only way to get 0 when you multiply. One of them has to be a 0. So in simplistic terms here it says if a times b equals 0, then either a was 0 or b was 0. That's just how it works if you want to get a 0. So they're going to start us off with baby steps here and say, oh, we'll give you a nice factored one and everything. Which of these is the correct solution to that little bugger? If x times the quantity x plus 1 has to equal 0, what are the solutions? If that x in front is 0, 0 times anything is 0. If we put a negative 1 in those parentheses, negative 1 plus 1 is 0. There's 2 zeros for that one. And And remember, when we're talking about quadratics, they might have 0 solutions, 1 solution, or 2 solutions. So just because we see 1 immediately doesn't mean we give up. Now, the quadratic they had us put in our calculator worked out very nicely. So that means it's factorable. So that's the way we want to solve it algebraically. So it says resolve it by factoring. Okay, start thinking. There is no greatest common monomial factor here. This is not a perfect square anything, but this shouldn't be too bad because there's only one choice for getting that 2x squared. 2x times x. And in the back, I needed to multiply to -2 and add to -3. So let's see, it would make sense that if we had -4 for outside times outside and put plus 1x for inside times inside, that'll give us our -3. Cool. So then I realized, well, then either this is 0 or this is 0. Now sometimes people have to write this one down and then they go, oh, it's -1/2. See that? But usually the second one, nobody writes this down. Well, it's 2. There's our zeros. Exact same information in calculator. Exact same. But this time we have the math to back it up. We can show them, hey, this is how it works. So, before we move on to extracting the square roots, because we haven't factored for a few days, give me your 43210 on your how you feel about your competence of factoring. I know you were doing really well before. That's what you were doing all kinds of factoring. So you think things are still going good? Excellent. Excellent. All right, because that'll be a part of the assignment that we do. Now this one says, solve by extracting square roots. What? When the dentist takes a tooth out, that's an extraction. Not that one. Extracting square roots is just taking square roots. That's what we're going to do. So to solve by extracting square roots, you must be able to write the equation in the form something squared equals something. That's what we want to do. Because if we have something squared, we can just take the square root of both sides. And that'll start that first process of solving. And remember, when you square root, whenever we write that square root symbol, we have to remember plus minus. These problems do not come all made for us as principal roots. We have to remember plus and minus. So this says, all right, let's just give it a try. Let's do some of this solving by extracting the square roots, by taking out square roots. Well, this first one is set up very nicely for us. So I look at that and I think, should I write out 2x minus 1 times 2x minus 1, FOIL that, and get 4x squared? No, silly Cedar Home. Do this instead. Take the square root of both sides. So now I have 2 equations that I can solve. And again, remember number line, we want that negative on the left. 2x minus 1 equals -3, and 2x minus 1 equals +3. Those are not going to be hard to solve. Add 1 to both sides. And divide by 2. Well, nice integers. Gotta love it. B. It doesn't look like that. No, but we're thinking, people. We know how it works. The book shows us something like this, and then the next step requires 1 step to get it to look like that. So I think, okay, so I had better be looking at a perfect square trinomial, or I'm not going to be able to extract square roots. So I wonder if this is a perfect square trinomial. Let's see. I can't factor anything out of all of those. This is a perfect square. This is 3x squared. And this is a perfect square. It's 5 squared. And I remember, to check the middle term, I have to take 3x times 5 and double it, and it has to match what's up there. Is 3x times 5 double 30? Cool. That makes it a perfect square trinomial. And we already know what needs to go in here. The 3x and the 5. And then to figure out if it's going to be a plus or a minus, all we have to do is look at that middle term. It's plus. Now it looks just like this one. So what would we do next? Square root of 2. Take that on both sides. 3x plus 5 equals plus or minus 6. Then what? Set up your two equations. 3x plus 5 equals negative 6. 3x plus 5 equals positive 6. And yeah, I know your heads are all down and you've already got the answers. Well, good. X equals 11 thirds. X equals 1. X equals 1/3. That's extracting roots right there. 4, 3, 2, 1, 0 mean extracting roots. I'm confident you feel like that. So if the problem says extracting square roots, solve this by extracting square roots. We can get those to be a binomial squared. Excellent. Excellent. So now what? Well, now is completing the square. Because this is a nice, easy process. We would like to do this all the time, if possible. And that's what's going on here. So this says the technique of example 2 is more general than what we see there. Because every quadratic equation can be written in this form. It just sometimes takes a little bit of work. The procedure we need to accomplish this is called completing the square. Here's the one glitch with completing the square. You must have a 1 in front of the x squared. It has to be a 1. If it's not, the first thing you do is divide out whatever that number is. Because the process of completing the square demands that we have 1 x squared. So if we're going to solve x squared plus bx equals c by completing the square, little itty bitty formula to remember, b over 2 squared to add to both sides of the equation. And then we can get it to be a perfect square. And we can take square roots. So x squared plus bx, add that b over 2 squared to both sides, because whenever you do the one, you have to do the other. After all, this is still algebra. And then we write it as a binomial squared. And away we go. We extract square roots from there. So b over 2 squared. Not a tough formula to remember. But like I said, sometimes when you don't use it for a while, you lose it. It's one of those things. So to solve ax squared plus bx plus c equals 0 by completing the square, we have to first divide by that a value. Because it needs to be a 1. It has to be a 1 to complete the square. And right away, they put our feet to the fire. Look at this. There's a 4 in front of it. Well, we can divide by 4. You're not scaring us. 4. There. Divide by 4. That's no big deal. Fractions don't scare us. Start thinking. Maybe this just happens to be a perfect square trinomial. Well, this is a perfect square. Ooh, that is not. So that 17/4, that's not helping me where it is. So what I'm going to do is I'm going to move it out of the way. And put it on the other side. So that I can get a number that will make this work. Good to see you. You too. So the next step is, that's our little b over 2 squared. So I realize it's ax squared plus bx, and I need b over 2 squared. So that's going to be negative 5/2 squared. Well, that's pure division. You can go ahead and distribute that power of 2. So that'll be 25/4. But what I do to one side, I have to do the other. That is still a basic algebraic principle right there. Now what we just did was we made a perfect square trinomial, which can be written as a binomial square. So I think, okay, what do you square to get x squared? X. What do you square to get 25/4? We just did that. That's over here. Negative 5/2. And then negative 17/4 plus 25/4 is 8/4, which is 2. Beautiful. Now we can extract square roots. So we're going to take the square root of both sides. And we're not going to forget the plus or minus. And we're going to realize, well, square root of 2 is kind of yucky. We can't put anything else with it. But what we can do is we can add 5/2 to both sides. So this says x equals 5/2 plus or minus the square root of 2. And we just found two answers. 5/2 plus the square root of 2 and 5/2 minus the square root of 2. Two perfect answers, by the way. We did not use a calculator to find those. We did not use decimals. If you did use a calculator, how could you know you're right? Well, you use the calculator, you write down the decimals that you get, then you plot 5/2 plus the square root of 2 equals into your calculator, and 5/2 minus the square root of 2 equals into your calculator, and you make sure that the decimals you got are the exact same decimals that you have there. So that's a good place to start, because that one looks a little scary. That's as far as I got with the other classes. So I'm going to give you the assignment. We won't be able to do the whole thing. I'd rather that you didn't do any really complicated completing the square problems until we work on one of those together. And yeah, this is going to look scary too. Because we want you to have a little practice at each of the skills that we talked about today. So there's not a lot of problems there you can do. What do we got? 3, 6, 9, 10. There's 14 problems that you can do. This is the directions. And I did put it on Schoology, so feel free to take pictures if you want to. X-intercepts on the calculator, intersections on the calculator. That's solved by factoring and solved by extracting finding square roots. And then tomorrow we'll hit that completing the square a little bit more. And my not so favorite quadratic formula. And then we'll talk about missing the tables and all that good stuff. I'll just scroll that up a little bit because my recorder thing is annoying. I must have squawked a little faster with you guys than I did with you.